So welcome to this online chemistry lesson on the rate of reactions. How do you measure the rate of the reaction? The rate of the reaction basically it's the speed, all the speed at which a reaction is taking place, and it is basically the reciprocal of time which a reaction is able to take. There are some reactions which take a long period of time to come to completion, and some reactions they take a short period of time. So what are some of the parameters to check when you are measuring the rate of a reaction? One of them is the volume of the gas, which is being produced per unit time or being consumed, especially if it's a reactant. Another one is the formation of a given mass of a precipitate in unit time. So the factors which affect the rate of a reaction, they are 1, concentration, 2, pressure, 3, temperature, 4, surface area, and a catalyst. So we're going to look at each of the factors and understand how they affect the rate of a reaction. Before we look at these factors, there is a concept which we call collision theory and activation energy. So this it's not the it is the molecular explanation to the reactions taking place and how reactions can be able to increase their rates or decrease. So first of all, for a reaction to take place, the reactant particles must have to collide. Another thing to note is that not all collisions will result in a chemical reaction. Collisions that result in a chemical reaction, they are termed as effective collisions or successful collisions. An effective collision can only occur when the reactant particles, number one, they have more than or equal to the activation energy, and they collide at the correct or proper orientation. So those are the three important points as far as collision theory is concerned. The number one, for a reaction to take place, the reactants must be able to collide. And for a collision to be able to occur, then it's only those collisions which have successful or which have enough energy, which we call activation energy, for them to be able to react. Activation energy is defined as the minimum amount of energy which reactants must be able to possess before they react. And for those collisions which now lead to the formation of a product, they are called successful collisions or effective collisions. And number one, those reactants must have enough energy, which you call the activation energy. And number two, they must collide at the correct or proper orientation. So this figure here, you can be able to see how the reactants are coming to each other. These are proper orientation, where this molecule, it is facing the bond here. It's going to break the bond between these two atoms, and then it's able to form new products. So if this orientation is not attained, then a successful reaction can occur. What is activation energy? Activation energy is the minimum amount of kinetic energy that the reactants particles need in order to have an effective collision. Now, this diagram here, it shows the energy level diagram between the reactants and the products. And here you can see this is an exothermic reaction because the products are on the lower side than the reactants. So before the reactants can be able to form the products, there is some activation energy. There is they must be able to climb this hill here, energy gap, before they can be able to form an activated complex. Then they can be able to react to give us the product. So this energy gap here, which is required before the reactants can be able to join together, is what we are calling activation energy. The activation energy is again shown here for an exothermic reaction. And for an endothermic reaction, it is this gap from this point all the way to this point that represents the activation energy before they can be able to react and they give you the product. So an activation energy is seen as an energy barrier which the reactants need to overcome before they can be able to form the product. So when you are going to explain each of these factors, you're going to explain them in terms of how they affect the how they can be able to affect the collision theory and the activation energy for the reaction to be able to increase or decrease. For example, we begin with concentration. The higher the concentration, the higher the rate of a chemical reaction. An increase in concentration of the reactants reduces the distance between the reacting particles, hence increasing their collision frequency to form a product. Practically, an increase in concentration reduces the time taken for the reaction to take place. Therefore, when you increase the concentration, you increase the rate of the reaction. We have an example here of a chemical reaction which can be done in the lab. And in this chemical reaction, you can be able to see a chemical called 0.05 molar sodium thiosulfate, which is placed in a beaker. And then before it's going to be reacted with 0.1 molar hydrochloric acid solution. But the concentration of sodium thiosulfate is going to be decreased continuously by adding water. So here you can be able to see that the experiment is done under different volumes of the acid and adding volumes of distilled water to be able to dilute it. So you can be able to see a sample result which has been obtained here, where we have the volume of the acid. For example, we add 20, then after that we reduce it to 18, we add some volume of water, reduce it to 16, add some volume of water, reduce it all the way to 10 and increase the volume of water. So students, you know, when you're doing these, you are actually doing what you're calling dilution. And then here we are also, but the total volume of the sodium thiosulfate is actually kept constant. This is to increase the accuracy of the measurements which are being done. Then the time taken for a mark X to be invisible, it's recorded here. And you can be able to note that the values have been recorded to the equal number of decimal places. So if it's 1 decimal place, and for most times, even 2 decimal places is actually encouraged. And then there's a column here for the reciprocal of time. So if the time is 20, you're going to have 1 divided by 20 to give you 0.05. So when these columns are filled like this, then you can be able to proceed now to be able to draw a graph. The first graph here is a graph of time against the volume. You can be able to see how the two are relating. And one of the questions you can be asked is to be able to explain how these two are relating. So you need to be able to understand, you can see the question there. Explain the shape of the graph, the graph which I've shown you on the previous slide, which is when water is added to decrease the concentration. So actually the answer here is trying to explain this curve here. It is that when water is added, it causes dilution, which leads to a decrease in concentration. So decrease in concentration reduces the rate of the reaction by increasing the time taken for the reacting particles to collide to form the product. So you can be able to see you are explaining the shape of the graph, but you've brought in the concept of the collision theory. So it's a very, very important theory which you need to understand. And then also a sketch of, if you try to now plot the volume of the acid used against the reciprocal of time. So the reciprocal of time is basically what you're calling the rate of the reaction. And you can see here it is, if you draw the baseline of it, is a straight line. And that one clearly now shows that the volume of the acid which is being used, actually, it's directly proportional to the reciprocal of time, or the rate of the reaction. And from the graph 2, you've been asked to determine the time taken for the cross to be invisible when the volume of the acid is 13 cubic centimeters. So you've learned the concepts of plotting graphs, and you can be able to see here that actually when you can be able to see here that when you interpolate, you come to the side where the volume is actually 13, then you just move across like that, you move across where it meets the graph, then you move downwards, that you are able to read the value down here. So approximately you can be able to read that value there. You get a value like you have this one here, 2.75 times 10 raised to power -2, or 0.0275. And then since you've been asked the time, and the graph here, it has we have used the rate, then you have to get the reciprocal of that rate, which has been done here, which is going to be 1 over the value which you have obtained, to give you 36.3636 seconds. So you can also be able to try the second one here. If you check when the time now, when the volume is actually 15, so you do the same, you move across. That's how you answer questions from a graph. You move across here, where it meets that graph, then again you move downwards, then you are able to read the value you get down there. Try to be as accurate as possible, especially if you have been provided with a graph paper. Therefore, like 0.3, this is 335, so something like 0.33. Then you can be able to get the reciprocal of that. So it has been shown how you go about that. And then I also want to show you guys how you can be able to get the concentration, especially when you're doing dilution. This formula is very important on calculating the change in concentration. For example, we use C1 V1 is equals to C2 V2. So for instance, in this question here, you can see the volume of the acid, it is 5, but the volume of water which has been added is being increased continuously. So therefore, you can be able to get the concentration of the sodium thiosulfate here, for instance. So if initially it was 0.4, and the volume it's 25, then you can be able to calculate the new concentration by putting C2, and the total volume has been added to 25. So the first concentration is 0.4. Then using the same formula, C1 V1 is equals to C2 V2. You can see that if the initial concentration is 0.4, the initial volume now has decreased to 20. You have 20 over here. Then the new concentration can be calculated, noting that the final volume is actually 25. So because 5 cubic centimeters of water has been added, so the total volume is going to be 25. So once that one is done, then you can be able to see that actually the molarity, or the concentration, it's decreasing. Take here, even when the initial volume is now 15, the initial concentration is 0.4, then it is diluted to 25. So you can see here, the volume of water added is 10, the volume of sodium thiosulfate is 15. When you add these two, you get 25. So once that one happens, then you can be able to calculate the changes in concentration as they move about. So it's important to remember this formula here when you are calculating dilution. So there's a lot of work you can be able to do as far as changes in concentration are concerned, but I've given that discussion at least to show how you can be able to plot graphs and be able to answer questions which may come after that. Another one I'm going to look at is temperature. So temperature, when you increase the temperature, you increase the kinetic energy of the reacting particles or molecules, and therefore you increase their collision frequency or the rate at which they are going to collide. Increasing the temperature, therefore, increases the particle which can overcome the activation energy. So basically what you're doing, remember the electrical hill which you're able to draw. When you increase the temperature, you increase the kinetic energy so that the molecules can be able to climb the electrical hill or that energy barrier, and they can be able to cross over to give the product. So each one of the factors you're going to discuss, you must bear in mind the collision theory and the activation energy. That a reaction can take place only if molecules collide. And it's only those molecules which have enough kinetic energy which can give successful reactions. So therefore, temperature increases the kinetic energy, and that one, they can be able to overcome that activation energy. So here there's a reaction between the sodium thiosulfate plus HCl to give you sodium chloride plus SO2 plus sulfur. So this chemical here, sodium thiosulfate, what you cannot see, it's Na2 S2O3. So usually it is used because of the formation of what you are calling the colloidal sulfur, which is the one which now obscures the beaker, and you cannot be able to see your cross X. So when you do this in the lab, you can be able to see that there is a yellow substance which is formed, and that yellow substance is colloidal sulfur. It's a yellow precipitate. Then we have a sample table here. So you can be able to see you have a table now when the temperature is increased from 30 to 40 to 50 to 60. And then we have the time taken for the X to be obscured. That means that colloidal sulfur or the precipitate to be able to be formed. You can be able to see that the time taken at room temperature, it is 50. Then as you're increasing the temperature, clearly you can see that the time is decreasing. And again, look at the consistency. If it's the time, it's recorded the same number of decimal points. Then if you get the reciprocal of time, now which is we're calling the rate, then you're going to have 1 over 50, 0.02, 1 over 40, 0.025, 1 over 20, 0.05, 1 over 15, look here, at least 4 decimal places, 1 over 10, 0.1. So if this one has 4 decimal places, it's advisable that you make sure that all the values in this row here, they have equal number of decimal places. So as an assignment, students try to plot a graph of temperature against 1 over T, which is the rate of the reaction, just like the one which I was able to do previously here. You expected to get a line similar to this one here now for temperature. So try to plot that graph and see what you get as an assignment. So when you explain the shape of the graph, we have indicated that it's going to be a straight line, indicated that an increase in temperature increases the rate of the reaction as the particles gain kinetic energy, therefore increasing their frequency and intensity of collision to form the product. So these questions, you can only be able to answer them once you've drawn the graph. So I'm going to skip them for now. Then another factor which affects the rate of the reaction, it is pressure. So pressure affects only gaseous reactants. So this one comes from the Boyle's law, in which it talks about an increase in pressure leads to a decrease in volume at constant temperature. So the decrease in volume of the container brings the reacting particles closer to each other, which increases their chances of effective. Another term you can use, successful. Another term you can use is fruitful collisions to be able to form a product. So an increase in pressure, therefore, increases the rate of the reaction by reducing the time for the reacting particles of gases to be able to react. So this one is very, very important. And as you have noted, it only affects gases because the position of their particles can easily be changed when you apply pressure. But for liquids and solids, you cannot be able to affect the position of the particles because they have what you call fixed positions. So even if you apply pressure, it cannot be able to affect their volume. Therefore, changes in pressure only affect gases. Some of the industrial reactions which are affected by pressure, one of them it is the Harper process for the manufacture of ammonia. If you can be able to see here, for you to be able to form the products, clearly you must be able to decrease the volume. Here you can be able to see 1 volume, 3 volumes, making a total of 4 volumes, and the product has only 2 volumes. Therefore, for you to be able to decrease the volume here, you must be able to exert pressure. The other one is the contact process for the manufacture of sulfuric acid. You can see here you have 2 volumes and 1 volume of oxygen, and the product has only 2 volumes of SO3. Therefore, for you to be able to form this product here, you must be able to exert some pressure. Lastly, if you are able to check here, this is 9 volumes of the reactants to 10 volumes of the product, and therefore here pressure does not really affect because they are almost the reactants and the products are almost equal. Good. Let's talk about surface area. So surface area is actually the area of contact between the reactants. An increase in surface area is basically a decrease in the particle size. So when you decrease the particle size, you can do that by chopping the particles, cutting the solid lumps into smaller and smaller pieces. You form what you call powder. So when you do that, the powder has the highest surface area, and an increase in the surface area increases the area of contact with the liquid solution, increasing the chances of a successful or effective or fruitful collision to form the product. So I'm going to show you in the next slide here. For example, we have a reaction between magnesium ribbon and hydrochloric acid to give you magnesium, magnesium chloride, and hydrogen. I've written this equation in ionic form. You can see that when the magnesium ribbon, it is just in ribbon form. The molecules, all the atoms which are in contact with the acid, they are very few. But when you chop it, when you decrease it, you form it into powder, then you are increasing the surface area, and therefore the acid can be able to penetrate deeper and be able to react with the magnesium atoms. Therefore, when you increase the surface area by breaking it into smaller and smaller pieces, you are able to increase the surface area. Now, I've been able to show a graph here. If you can be able to see these two reactions here, this is the volume against time from the start of the reaction. So in these two reactions, you can be able to see that the volume produced is the same. This is very important. But look at where the curves are flattening. For a smaller surface area, you can be able to see, especially if it is lump sum, it is taking a long time before the reaction can be able to come to completion. But if you break it into smaller and smaller particles, you have a very small surface area like in a powder, then you can be able to see that the time taken, it is very, very short. Therefore, these two graphs, they actually show when you decrease the surface area, you are able to increase or to shorten the time required for the reaction to take place. Therefore, that is actually what happens. Increasing the surface area decreases the time required and therefore increases the rate of the reaction. If you can also look into the catalyst, the catalyst can be able to increase the rate of the reaction. We have biological catalysts which are called enzymes, and basically catalyst can be able to increase the rate of the reaction. A catalyst has no effect on the enthalpy of the reaction, but it lowers the enthalpy of the what you call the activation energy for the reaction to be able to proceed very fast. On this graph here, you can be able to see the energy, the activation energy for an uncatalyzed reaction is very high. But for a catalyzed reaction, you can be able to see when a catalyst has been used, it reduces this activation energy so that the reaction can be able to progress much, much faster. Some catalyzed reactions we have, it's like the contact process, where the catalyst used is vanadium 5 oxide or platinum. But you know that platinum is it's a bit expensive and susceptible to impurities. Therefore, vanadium 5 oxide is most preferred in that. So to reduce the industrial cost of the manufacturing sulfuric acid, then a catalyst is used. Vanadium 5 oxide is used because it's cheaper, though it is easily susceptible to impurities. In the Oswald process, we use the platinum rhodium to be able to catalyze that reaction there. And in the Harper process, which is the manufacture of ammonia, we use platinum or iron catalyst to be able to do that particular reaction. So thank you for your time. That is the lesson which you've had. I can see my sister on that end. And